virtually. So yeah, so maybe for some of you it will be repetition of what I said if you attended the last setup lecture. And maybe in a sense it is good that you will be you can ask me more informed question and we can have a better discussion in that way. So yes, with that, let me just quickly show you what I think I have three. Sakat, can you remind me, three or two or
Four
four
lectures,
lecture? Okay, four
yeah.
lecture. Okay, all right. So let me start sharing the screen. Share screen. Share. All right. Okay, so the first thing I would show you the outline what I plan to cover. It's kind of so don't get bit like it's too many things, but it is like each of the slide. Let's say the title of the slide. Sometimes I have written it in terms of outline. So basically, what is machine learning? And why machine learning in high energy physics, and the two of the things that you all would be using in linear regression and classification scheme, and what we call supervised, unsupervised learning. The main intention of this four lecture is essentially to try to break the jinx. Sometimes people call machine learning or all these different type of machine learning technique as kind of black box. So I try to give you sort of how to break up this black box and sort of go in bits and pieces. Obviously I'm not an expert in that sense, so if we have some questions and that part I don't understand, we'll also try to understand in the process of giving the lecture. And then some of the essential aspect that goes under the scene, like when you're doing this modeling the supervised learning, what are the parameter you're trying to optimize on, and how do you validate that process? All these things you do, like if you have done in your analysis or a study, let's say anything with a neural network, or let's say boosted decision tree, or even Fisher discriminant in any of these analysis. Yeah, so in the part two, we will talk about what is neural network. Quite likely all of you would be knowing. And again, sort of deconstructing back this different type of neural network and the underlying ideas, and then the boosted decision tree, the different type of boosted decision tree. Largely speaking, in your analysis or most of the things you'll be doing, if you're doing a sort of a machine learning technique, you'll be mostly dealing with this kind of two method. But then there is something more. If you're talking of these days, you're talking of deep neural network, going further down, and there are CNN convolutional. I mean, there are more fanciful method also. For example, you'll see soon that somehow high energy physics is kind of, although this method is more like the computer scientists they have come up with, but I think in high energy physics, in big data science, they have used that, and then it has percolated to many other streams. Obviously, like it is more like the computer scientist job in the concept and things like that. But we have been high energy physicists. We have been one of the main sort of, you can say, the driver of these methods in the big data science. Okay, so with that much of thing on the outline, let me just go to the business. Right. Okay, let me try to make it full screen. Okay, so so I think the first point is, what is machine learning? That some of you might be thinking, what is this a big deal? I mean, machine learning, what? So in a sense, it is it is giving your computer, which is acting as a machine, right? Giving its ability, giving it some kind of possibility to learn from data directly without explicitly programming them. So normally, as you know, computer is a DOM. I mean, in the sense that you have to program the computer, right? That's normally we do. And be the operating system, be, I mean, you know, so sort of, then you have the programming language. So here, you are basically letting your computer learn, letting your machine learn based on the data, and that data, so that the machine is now adapted, or kind of trained to sort of be able to operate in new kind of data. I mean, imagine this, like when you are a kid, you didn't you didn't know how to speak, you didn't know what is what in terms of color, you didn't know what is how's this food, how's that food, and you have been trained, right? I mean, your brain from very early childhood, your parent, your brother, sister, if you have, I mean, they continuously tell you this is that, this is this, and you get in the process, you get trained, right? And you know the story of that I'm forgetting the human kid taken to jungle, and then with living with the gorilla and tiger and all this thing, after several years also behave like the tiger, and making the sound, and so it's exactly like that. You let the computer is that, let's say, human baby, where you're showing, you're teaching the computer with different kind of data in for certain to do certain thing. And yes, so and how it is done, and this is not like, this is all underlying things, statistics, there is a computer science, the probability, and at the end of the day, we are doing an optimization. I mean, normally, if you have some, you are all familiar with root or any other data analysis framework, like you have some data, and you try to fit it, right? You do a chi-square fitting, many other kind of fitting you do. Or you have some kind of cut optimization, you have some selection variable, and you want to optimize on that, you try to maximize your sensitivity. So that is like in sort of one dimension or two dimension. Here we are talking of multi-dimension. When I say, it's like depending on how complex your data is, okay? So you take the data as, it's a like, you can see, you start with the data and let computer learn from the data, right? So that computer knows what is that pattern, what is the regularity, and if you have multiple variable, what is the relationship, and then once the computer is well acquainted with that, then you are just applying to different kind of data. So what is the machine learning used? There is several things. We, from high energy physics point of view, we are in the bottom of the thing, as you can see, the data science, big data science, very complicated data structure, and we are using machine learning to kind of doing the thing properly. But then you can see, this is one thing, I guess you should all be proud of, that if we capitalize, or if we kind of do this thing well, in future, if you wish to move out of academia, you have this next we are already into this so-called machine learning, artificial intelligence age, I would say. So there are several things, this natural language processing, speech, handwriting recognition. Some of you might be knowing that we get some very old script and a machine learning technique are used to identify what are those things. Object recognition, computer vision, financial market analysis, many other things, and more importantly, recently with this Google and other self-driving car, right? I mean, you would all love to have your self-driving car, and you just tell, drive me to Bombay to Calcutta or whatever. I mean, so it's like really going in the highway, or Bombay to Delhi, or Bombay to Pune, something like that. Yes, so let's now get into that part that we use in high energy physics. Okay. If you feel like interrupting in between, so please do so. And if you think I'm going too fast, also let me know. I don't care much to cover everything. I would rather like whatever we cover, you rather understand and appreciate that. Okay, so that's the idea of this lecture. So machine learning techniques have been used very widely in high energy physics. Okay, and in this so-called physics analysis, where mostly you are interested in finding out what we call a needle in the haystack. Like, you know, there's a huge background, and then you are trying to find out the signal, and especially if you have highly complex final state. And then sometimes you have sort of heavy resonance. You want to sort of get a better mass resolution, the energy resolution, momentum resolution that you want to improvise. Before going to higher level analysis, where analysis are mostly done with the higher level object, as you know. Okay, we call it electron, call it muon, call it, if you're dealing with jets, hadronic jets, you call it photon, so on and so forth. But then in the reconstruction, that where you get the detector level, very basic input, from there you want to go to the next stage, which is the higher level object, right? You, in your so-called tracker, you get hits, right? So I understand in Alice you have TPC, or okay, I mean, I think, or whatever your tracker is, gas-based detector or silicon detector, you get hits, and out of the hits, you want to build up the track. In your calorimeter, you have the energy deposit. From that, you want to find out so-called clusters. And then if you have charge track, you want to identify whether it is a pion, kaon, particularly, or proton, charge hadron identification. You want to find out calibration, energy direction calibration. So this is more on the so-called the regression techniques. Anything classification. So basically the two things we'll mostly deal with high energy physics is either classification or regression. You also deal with trigger. I mean, particularly in a hadronic machine such as LSC, and in future it will be even more so in the FCC, Future Circular Collider, if it comes up. You have really complex final state, and at the data acquisition level, at the trigger level, you want to be as smart as possible, because you don't want to keep everything for all good reason. You want to be very selective with your trigger selection, online selection. Also, in computing, we use it. Even you can use, if you are doing lots of event generation, you can rely on the machine learning technique in optimizing, not optimizing, like facilitating is the faster turnaround time for your Monte Carlo generation. Like let's say if you are doing a heavy ion event, generating heavy ion event, it will be very complex for you, right? I mean, I don't know, like for event, maybe it's taking quite a bit of time. Now, in this process of event generation, if we know that what are the key steps and which steps you are taking more time consume, you're consuming more time expensive step. If we can do that, let's say it may be this multi-phase space integration. And can we break it up, and can we use machine learning there? Can I get a better time benefit? So these are the things, so as you save time, it is effectively saving the public money, right? Because your effective time taken for the event generation will substantially reduce. You will be more effective, and you will with a less computing power. Okay, so what is the key element in machine learning is a mathematical model. All right, so it's a mathematical model, and you have a system of interest, and you want to characterize this system of interest mathematically by the help of few variables. So what we call physics observable. Now, this what type of model, what type of mathematical model you would like to use depends on the task, or the depends also the complex data size you have. So it's kind of you don't have one model working for all, right? So that is as simple as it can get. So I said we mostly deal with two things. One is classification. So here you can see in this cartoon, you have two so-called random variable, physics variable, x1, x2. And here you see there are two class of events you have, and you want to distinguish them. Okay, you want to classify one against the other. The other one, you want to do regression. Here you want to model your be it some resolution, be it whatever your function in the y-axis you have, and as a function of a set of input variables. So this is more like fitting, but then it is not like fitting like the way you do in root, like you have few data and you fit it. So this is like based on the data machine learning technique, you are trying to get the best possible model to fit this 7 data point, or I don't know if there is one more data point missing there, but yeah, this kind of structure. Okay, you want to build that. The other thing we also do, this is called clustering. So you can see here that you have kind of two kind of lump. If you see the middle bottom plot, there are two this kind of structure. You see that's a data distribution you have, and you want to basically identify two such blob, two such cluster, because so initially you start your red and blue cross mark you see, and then in the process of multivariate, in the process of machine learning technique, you want to really identify one of the cluster with one and the other with the so basically two cluster. And the second thing we do, dimensionality reduction. This is like if you want to take an example, the simple example I can give, like you have xy or xyz. Let's take the two-dimensional case xy, and then if you model them in terms of polar coordinate, what we know of r sine theta, r cos theta, x r cos theta, y r sine theta, you already see that effectively we are reducing a two-dimensional problem xy into a single dimension, because theta is a cyclic coordinate, right? So r is the only variable that we worry about. Otherwise, theta goes from, it's a circle, right? So that's the point we're saying. Okay. So three steps, three keyword: mathematical model, second keyword learning, third keyword prediction and inference. All right. So these are, and at the end of the thing, at the bottom of everything, you have data. So first you want to model this data, and you want to first let your computer, let your machine learn to estimate given this data. You want the computer to learn from this data through various statistical modeling and get the best possible modeling. When I say best possible modeling, obviously as an experimentalist, I hope all of you or most of you are experimentalists. Anything you give, there will be some uncertainty, right? There will be some degree of ignorance that we say either statistical, obviously data size, systematic, the related to your instrument, related to your model, and other stuff. So that goes into your uncertainty. So similarly, when it's a best possible model, there of course it is, it will come with some degree of uncertainty. But never mind, that is the best possible thing that you can do at that stage. And once your machine has learned, the second, third stage is to make prediction or to make inference of new data point. All right. So that's the thing, as you know, in a supervised machine learning method, it's called, it is actually supervised machine learning method, where you have the so-called training and testing phase. Okay, so we talked about mathematical modeling, and now the second thing will be, so I think I have to close, if I remember correctly, at 4:40, right? Sorry, 4:50, is that right, Saika? 4:55 or something like that, time-wise.
You have time till 4:45.
4:45. Okay. Yeah. No
but
worry.
you can take more 10 minutes. No problem.
No issue. I will be.
Okay.
I'll stop and then I'll continue next time. Yeah.
Okay.
So
Yeah,
that
you
is
have
where
4 lectures. Yes. Yes. Yeah.
correct. Correct. All right. So the prediction and inference. So here you from the previous stage, which is in the learning stage, you have your computer trained based on the data, with using various statistical model. Now, given the thing, it is like if you go back to your own thing, like we're talking of human baby. So once you have trained the baby, this is red, this is blue, and this, and then you basically let the test knowledge of the, I mean, how far the baby has learned, right? So you can get to a different point. So in this stage, you use that statistical model that is already well trained on the previous stage to make prediction as well as infer properties of new system, new data point. So therefore, the modeling, the first thing you have parametric model. So there are two things you would have done, many of you would have done, all of you would have done that data point, given a data point, you fit to Gaussian, you fit to exponential, fit to polynomial set, all right? So there you have parametric model. So you are expressing the data with a fixed number of parameter, right? So for Gaussian, you have basically two parameter, mu and the sigma. Depending on Chebyshev, what order the Chebyshev is, which order polynomial is, you know how many parameter will be. If it is exponential, there is one parameter, and so on and so forth. But then you also have the case, I guess some of you would have done in the data analysis, that you don't get a good parametric model. So you can use directly the non-parametric model. Some of you might have used histogram set, or the so-called various kind of rookie PDF or something, which is smoothing the histogram. But these are the model where you don't have fixed set of parameter, right? So you, and then that complexity of non-parametric model grows as you get into more and more data point. Okay, so here you see in the top plot, the data point where you have sum of three Gaussian of different mean, all right? And in the bottom, you see non-parametric model where we're just taking that entire data distribution. You have blue point, I'm sorry, the red point and the green point, and trying to make a decision boundary out of it. You can easily see the kind of decision boundary you have got. It is quite non-conventional, in the sense it is not something you can do parametrically. Okay, so in one slide, if you want to sort of say that what is this thing, so you have a training data, and you use the training data to form a model. And once the model is formed, then you go to the model evaluation. You can use the same thing to test it, but more importantly is very, very important to have an independent test data structure, which has no way has biased on this training. It's like totally independent, right? It's totally independent, like the thing that we have been following in science, peer review, right? You never will have your supervisor kind of looking at your thesis as the external examiner. You will never have your collaborator reviewing your own paper, right? That's a conflict of interest. More importantly, it will have the bias. It will have the bias. So you always have the peer review, independent referee. So that is what is the test data says. The test data doesn't know that how the training was done, how the model parameter were built, but it's an independent data set, equivalent data set. Now, the performance that you will be getting from the training data set versus the testing data set, they should, if you're modeling, if your training is what we call properly trained, not under trained, not over trained, then you should get consistent 45-degree slope one, sort of if I'm putting the output of the training data versus the testing data, they should be all in the straight line of slope one. Okay, so yeah, so if you have any question, pause me, ask me. But yeah, so there are two kind of learning. three, but we do not deal so much on the third category called reinforcement learning. So most of us will deal with the supervised learning, but some of you might be also dealing with unsupervised learning. So supervised learning, we discuss very like where you have signal to background, separation, classification, or given a track, given some of the so-called observable, like let's say specific ionization, let's say the time of flight, let's say the Cherenkov photon coming out of this track charged particle going through a detector medium, like deciding whether the track is a pion-like, more pion-like or kaon-like, what you call the particle identification. And then the regression, right, where you want to do the functional, like you have the data and you want to model the data as let's say resolution or yeah, or like yeah, something like that. So that is the data regression. On the unsupervised learning, so between supervised and unsupervised, there is a key difference. The key difference is supervised, you have some kind of label, right? When you do, like, it's like the way we teach our key, right? We little bit, we should not supervise too much. Like sometimes let them make mistake and then we correct. But then, you know, we tell them this is correct, this, you go on this side of the road, you know. So you supervise, you tell what is correct, what is wrong, you tell what is what, right? So in the supervised learning, you tell that if you have the distribution like this, it is like signal. If you have distribution on the other hand like that, that is the background. So there is a kind of labeling is already there, right? So that goes into the learning process. In unsupervised, you don't do that. Okay, you provide the data for sure, but you do not label what is what, and that done differently. And that is so the labeling part is specific to the supervised learning. So in unsupervised learning, we have clustering and the dimensionality reduction. We just give a few example of that. Let's say in the Fisher discriminant method also it is done, like you have several input variable and then you want to get a linear combination into so you have n-dimensional hypersurface, you go to one dimension, like finally you have got one output variable. So it's like the input variable you have, let's say xi. So you are basically summing up alpha xi and then you are optimizing on the alpha I. So that is a kind of dimensionality reduction. Okay, so here are some notation just to tell that what we'll be using this word in next few slides. Like bold uppercase, that is matrix, lower bold lowercase, that is a vector, lower standard face, not the bold face, that is the scalar, and so on and so forth. Then you have the labels that we said that would be useful when you go for the supervised learning. And then you have what we will call, time to time we call it variable, physics observable, that is also called feature. We'll also call them input to the machine learning technique. Then you have, when you have a data point, x1 going to xn, that's called n feature, right? I mean, if you have sort of n discriminating variable that you add, obviously your data may have more than that, of course, that you don't want to explore, but at least for your analysis, I want to sort of find out these are the variable that I want to deal with for my signal to noise separation, or for my particle identification, or for my energy resolution calculation. And then the other thing is, given this end feature variable, you want to get into the, you train that what you see WT, that is what we call weight vector. So that is part of the process of the training, and that W0, that is an offset. And in the process, you are going from X to Y, all right? So this is what, so one of the thing I should say that the black box of machine learning, you should not get, oh, okay, it's a big deal. So it is a multidimensional optimization. It's nothing more than that. It is a multidimensional optimization problem, nothing more than that. Okay, it's just the fact is how it is optimized, like, what is the level of complexity, and those are the detailed part, but it is as simple as it is a multidimensional optimization. So just the previous speaker was talking about the bias theorem. So the joint PDF, the conditional PDF, conditional, like what is the probability of Y given X, and joint distribution, what is the probability of X and Y, and then the so-called marginal probability, what is the probability of X. So then you have the Bayes theorem, that is really an important component of the machine learning technique. It goes very much in all aspects of the machine learning, really the important aspect. And then you have the expected value for a function. And okay, so that these are certain things, normal distribution, Gaussian distribution, then Poisson, and those things. All right, so let me just try to finish with supervised learning, and then we will stop there to take up any question, because I still have 10 minutes. So supervised learning, here what we have. So, given you have n possible examples, n possible classes, the n could be 2, that is called binary classification, but n could be more than 2, that is called multi-classification, multi-class classification. All right. Now the feature, again, I go back, we say that sometimes we call feature, sometimes we call input variable, sometimes called just inputs. So you have several feature that is basically part of that set, the calling X, and the target. So you want to get, given this feature, you want to get the target yi, and this yi could be just 0 and 1. Let's say if you're doing binary classification, you have just 2 class, either Higgs boson, Higgs signal, or all the standard model background, okay, signal background, or there is, you get an output for each of the, let's say, a class, and then given this multi-class, then you can formulate out of that, you can get the let's say binary thing. So I don't know, probably some of you would be knowing, or maybe all of you would be knowing heavy flavor tagging, B tagging. I'm sorry, I don't know if it is very much used in Alice, but I assume it is used. You have some way of identifying so-called beauty event, the B tagged event or B measured event, versus there is a charm tagging event, and everything else, UDS, those kind of event. So here you can see there are 3 classes of event, and the difference between the beauty and the charm event, that the bottom measure fly a little longer. I mean, it has a lifetime larger than that of charm measure, and it flies higher, longer distance. So therefore, both the cases you have secondary vortex, but charm will be closer than the bottom. All right. So that part is exploited in this multi-class classification, and you see B to C versus B to other. Obviously, you can do, so there's a 3 class I'm talking about. So you can have more number than that, 3 of course, but these are multi-class classification. And it is expected that all those input variable, at least if not all, like if you have multi-class classification. In binary classification, for sure, all that feature variable you will be taking, they must contribute something, right? In case of multi-class classification, your number of feature variable, of course, fixed. And it is likely that between class 1 and class 2, you may have, out of n variable, you may have m number of variables showing some separation. n minus m, they may not have a separation, but that n minus m have may have something to do while separating C2 class 2 from the class 3. I hope it is clear to you what I'm trying to say. In case of binary classification, whatever set you are taking of set of feature, they have to have really something to contribute. You don't want to add so-called noise variable. If some variables was identically same discrimination power between signal and background, obviously you're not going to use it. In multi-class classification, on the other hand, you have that same number, but then not necessarily all of them will be helping for each class of separation. That's the point. Okay, so regression, here you're going into that levels, and here your y is a real number. You are getting that function. Okay, yes, and so then you have the various discriminating model, and yeah, so this is like what you know from the base theorem, and sometimes we use this so-called conditional density and prior to compute this distribution. Okay, so that goes under with the classification of regression. Now, very quickly about the unsupervised learning. Here you have some data, okay, with the feature xi, but here there is no label. In the earlier case, you saw in the classification case, you had labels. Okay, in regression, it is like you are doing y as a function of x. All right. So here you have no label, but you let the machine learning to find some structure. Okay, so what you would like to do, if you would have known the jet clustering, like you have the energy deposit in your calorimeter, you have some related track in your tracking detector, so you can know whether it's a neutral particle or the charged particle. And then given this thing, you want to find out the so-called the jets, right? Hadronic jets, so cluster of particle. So that kind of partitioning of the data into groups, right? How to make the group, where to stop it, those come into picture, right? So there is certain technique, and that's like from the data you are trying to learn that. Without that, you don't know that how many, and there is no labeling here. Dimensionality reduction is basically given the data, you want to go from one, I mean, the input variable are there. From that, you want to go to a lower dimensional representation. I gave a simplest example of how to reduce from a 2-dimension into a 1-dimensional problem. Okay, so I think I will stop here. I don't want to go any longer than that. And I would like to use the remaining 3 minutes or something. If there are any questions and comment, that is what I would like to use. Yeah, because this reinforcement learning, we will not use it. So this I will take it off. But yeah, Sarkat, I am ready to take any questions, comment.
So yes, is there any question from students?
Actually, evaluation, I know Sarkat had done this some time ago. So evaluation of the student for my lecture will be whoever asks question get good score. Whoever,
yeah, that is the best thing to judge a student.
Right. Right.
Yes.
So yes.
I always, I have seen that students from IIT Indore, they usually ask questions. So
so yes, so they asked
actually,
quite a few questions last time, but this time let's see, either indoor or other. I mean, yes. So let's see.
No, IIT Indore students are very interactive, so they are very.
Okay.
Yeah. Bhagirathi, any question now? Any question? Hirok
Yes.
will ask question. Yeah.
Sir, if we actually, sir, it is a maybe comment or something. Actually,
Yes.
if we wish to calculate a impact parameter from the machine learning, can we go with supervised learning or it is unsupervised learning?
Right. So that will be exactly regression that I was talking about. Let's say, so it will be supervised. It is regression. Like let's say I said you have the data distribution and you want to find out the energy resolution, right? You want to show your, but then you also have the primary vortex, or what we call the pile up, right? And yeah, I'm sure you all, pile up vortices to identify that. Or let's say you want to, given this distribution, you want to find out the impact parameter as a function of something, right? So that will be more like the, of course, like this impact parameter, that what you are saying, you want to reconstruct it, but you will be reconstructing from something, right? So it will be more like regression, if I got your question correct.
Okay, sir. Thank you.
Any more question?
Okay, so the thing is, if
And
you
sir,
don't ask, yes, go on.
And sir, one more thing, sir. In case of supervised learning and in case of unsupervised
Can
learning,
you switch on your video? I mean, it is good to at least whoever is
actually, I
asking
am not in
question.
a proper place to switch on that. It
Acha,
is sorry,
ठीक
sir.
है. No issue,
Uh,
no issue. Go
so,
on, go on.
sir, sir, I am questioning about that. In case of supervised learning or in case of unsupervised learning, the required number of data, which is the efficiency in this case.
Hmm.
So,
How
my
do I
question
determine?
is,
Yeah,
yes, sir.
sorry, you go
How
ahead.
do it? Yes, sir.
Very interesting, very important question. But you will wait for like next lecture or something. That we will definitely come to that. Like at the end of the lecture, if you think this question is not answered, you definitely complain to me. Okay. So question is, what is the data size? How would I determine the data size?
Yes, sir.
You say like, you have very scattered data. Can I use it for this? I'll tell you the most important thing is, um, uh, if I can do a job, you have a nail, you want to put a nail in your wall, right? You want to put a calendar or something in your wall. So what you will do? What is the toolkit you will use? You take this what is that called? A hammer, or so what I'm trying to say, depending on the complexity of problem, it is not fanciful to say कि सारे जगह पर machine learning चलेगा, or is it like you have to see whether it is you need machine learning to do the job. Do I really gain anything out of this? This is the point you want to do. So it is not like हर कोई problem में you add machine learning, you want to apply machine learning. That is not the thing. So what I'm saying, you need to have enough data, like that's the question that you raised, that will be clearer soon, that where you can use it and what is the data size you need it to get best out of it.
Okay, sir. Thank you, sir.
Okay, so if there is no more question today, students